In chapter 5, module 2, we shall solve Abel integral equation by using a technique based on Laplace transform. Now, the theory of integral transform, or in particular Laplace transform, you will learn later on, but before using Laplace transform, I will give you a brief introduction of what is Laplace transform. Now we use Laplace transform technique. First, we define what is called Laplace transform. The Laplace transform of a certain class of function phi x or fx is denoted by L of phi x or L of fx. We have written it together so that the notation is L of phi x comma fx, and Laplace transform of phi x or fx gives a function capital phi of s or capital F of s, which is defined as integral 0 to infinity phi x e to the power minus sx dx. This is the Laplace transform of small phi x and denoted by capital phi s, and integral fx e to the power minus sx dx. This is the Laplace transform of small fx and is denoted by capital Fs. Here s is a complex number such that real part of s is greater than delta and delta is a positive real number. Now, to obtain fx or phi x, we need another formula called inverse formula for Laplace transform, which is denoted by the notation L inverse of phi s or L inverse of fs. So, by inversion formula, phi x is obtained as the integral 1 by 2 pi I integral gamma minus I infinity to gamma plus I infinity phi s e to the power sx ds. Similarly, fx can be obtained by the inverse formula 1 by 2 pi I integral gamma minus I infinity to gamma plus I infinity fs e to the power sx ds. Here I is the imaginary unit and gamma is a constant which is greater than the real parts of all singularities of capital phi s and capital Fs. So, this is the Laplace transform of a function together with its inverse formula. In equation 5.21, the constant gamma which is used can be different for taking inverse for phi s and taking inverse for Fs. Next, we define convolution of two functions small fx and small gx as integral 0 to x ft gx minus t dt, and this is denoted by the notation f star g x as given in equation 5.22. If we take Laplace transform of convolution of small f and g, we denote it by the notation L of f star gx, which is given by double integral. The outer integral is with respect to x with range from 0 to infinity, and the inner integral is with respect to t with range from 0 to x. Here the integrand is ft into gx minus t e to the power minus sx. If we interchange the order of integration and substitute p for x minus t, then after simplification we will find that Laplace transform of convolution of two functions small f and small g is equal to product of capital Fs and capital Gs, where capital Fs is the Laplace transform of small fx and capital Gs is Laplace transform of small gx as given in equation 5.23. So, this much of Laplace transform we will require to solve the Abel integral equation. Now, in 5.23 we have seen that Laplace transform of convolution of two functions f and g is the product of transformed function fs and gs. So, we can get back the convolution function f star gx by taking Laplace inverse of capital Fs and capital Gs, its product as given in equation 5.24. Now we come to Abel integral equation in its simplest form, which is given by equation 5.25. Here the kernel is 1 by root over x minus t, and the range of integration is from 0 to x, and phi t is the unknown function, and f0 equal to 0. Now we will take Laplace transform of equation 5.25. That is, we will multiply both sides of equation 5.25 by the function e to the power minus sx and integrate with respect to x from 0 to infinity to obtain equation 5.26. Here capital Fs is the Laplace transform of small fx. In equation 5.26, you notice the inner integral, which is 0 to x integral phi t divided by root over x minus t dt. Now, recall the definition of convolution of two functions as given in equation 5.22, which is integral 0 to x f t g of x minus t dt. Now, if we come to equation 5.26, we can see that the inner integral is the convolution of the functions phi t and 1 by root over x. So, left hand side of equation 5.26, you see that it is the Laplace transform of convolution of the functions phi t and 1 by root over x. So, we know that Laplace transform of convolution of two functions is the product of transformed functions. So, we can write 5.26 as capital phi s into capital M s equal to capital F s. Here capital phi s is the Laplace transform of small phi t and capital M s is the transformed function of 1 by root over x, and this is given by root over pi by s, where real part of s is positive, as given in equation 5.28. If we take Laplace inverse of ms, then we get back the function 1 by root over x as given in equation 5.29. So, from equation 5.27, we see that capital phi s is given by capital F s divided by capital M s. Now, the right hand side, capital F s by capital M s is a known function. So, in principle, taking Laplace inversion, we will get small phi x from 5.27. Now, this can be simplified. So, capital phi s is given by capital F s into root over s by pi by substituting the value of ms from 5.28. This expression can be alternately written as given in 5.30. Here we have taken out s by pi outside, and inside the bracket it is the product of capital Ms and capital Fs. We call this function capital Ms into capital Fs as capital Hs, and we assume that capital Hs is the Laplace transform of certain function small hx, so that capital Hx can be obtained as Laplace inverse of capital Hs, that is Laplace inverse of capital MS into capital Fs. We see that from equation 5.32, Hx is Laplace inverse of product of two transformed function. And if you recall that Laplace transform of convolution of two functions is the product of transformed functions. So, Laplace inverse of product of transformed function gives back the convolution of two functions. So, we can express Hx as the convolution of functions, which is the inverse Laplace transform of capital MS and inverse Laplace transform of capital Fs. And this is given by small hx is equal to 0 to x ft by root over x minus t dt. You may recall that capital MS is the Laplace transform of 1 by root over x. So, using the convolution we get Hx as given by 5.33. So, with this small hx, we see that capital phi s is s by pi capital MS into capital Fs as given by 5.30, and this product of capital MS and capital Fs is Hs. So, we can write phi s as 1 by pi s of Hs. Again we simplify and we consider Laplace transform of dH dx, where h is given by 5.33. So, if we perform integration by parts, then we see that Laplace transform of dH dx is given by s capital Hs minus small h at x equal to 0. Now, from equation 5.33, we see that h at x equal to 0 is equal to 0. So, that Laplace transform of dH dx is equal to h s into s. Hence, dH dx is Laplace inversion of s into capital Hs. Now, from equation 5.34, you see that s into capital Hs is given by pi into capital phi s. So, from equation 5.35, we find dH dx equal to pi into Laplace inversion of capital phi s. Now, in equation 5.35, capital phi s, its Laplace inverse is small phi x. So, from equation 5.35, we find that small phi x is equal to 1 by pi dH dx. Here hx is given by equation 5.33. So, the solution phi x of Abel integral equation can be obtained by substituting hx in the expression phi x equal to 1 by pi dh dx to obtain phi x as given by equation 5.36. So, this is the solution of simplest form of Abel integral equation. Now, we shall consider a more general form of Abel integral equation, and we shall use Laplace transform technique to solve this more general form of Abel integral equation. Now, we consider the integral equation as given by equation 5.37. Here the kernel is given by 1 by x minus t to the power alpha, where alpha lies in the interval 0 to 1 and f0 equal to 0. We have already defined the Laplace transform of functions phi t and ft together with its inverse formula, and we also have defined convolution of two functions and their Laplace transform. Now, we multiply equation 5.37 on its both sides by the function e to the power minus sx and integrate with respect to x from 0 to infinity to obtain an equation which is given by 5.38. Now, in the left hand side of equation 5.38, the inner integral, that is t integral, you can see that it is again a convolution of two functions phi t and 1 by x to the power alpha, and left hand side of equation 5.38 is the Laplace transform of convolution of two functions phi t and 1 by x to the power alpha, so that it can be written as capital phi s into capital Ns equal to capital Fs. Here capital Fs is the Laplace transform of small fx, capital phi s is the Laplace transform of phi x, small phi x, and capital Ns we denote the Laplace transform of x to the power minus alpha. So that in equation 5.40, the Laplace transform of x to the power minus alpha can be calculated to be equal to s to the power alpha minus 1 into gamma 1 minus alpha. Hence, if we take inverse of s to the power alpha minus 1, we get back x to the power minus alpha by gamma of 1 minus alpha. Hence, from 5.39 we can write capital phi s as capital Fs divided by capital Ns, which can be written as given in 5.42. We take capital psi s equal to s minus alpha capital Fs, and capital psi s is the Laplace transform of certain function small psi x, say. So that small psi x is given by Laplace inverse of capital psi s, that is Laplace inverse of s to the power minus alpha into s, Fs. Now, in equation 5.43, Laplace inverse of s to the power minus alpha into capital Fs, this is the product of two functions s to the power minus alpha and capital Fs. S to the power minus alpha is the Laplace transform of certain function which can be calculated from equation 5.41, and capital Fs is Laplace transform of small fx. So, product of two transformed functions, their Laplace inverse can be written as the convolution of the corresponding functions, and which is given by the right hand side of the integral, right hand side of the equation 5.44, and this function is given by psi x. Right hand side of equation 5.44 is written as convolution of functions fu and x to the power alpha minus 1. Now, see that capital phi s is written as given in 5.42, which can be written as 5.45, where we have taken s to the power minus alpha into Fs as capital psi s. Now, we take Laplace inverse of equation 5.45. The left hand side is capital phi s, whose Laplace inverse gives small phi x, and right hand side is 1 by gamma 1 minus alpha into Laplace inverse of s into capital psi s. Now, we calculate Laplace transform of ddx of small psi, which is given by s into capital psi s minus psi 0 by using integration by parts. We see from 5.44 that at x equal to 0, psi 0 is 0. So that s capital psi s is Laplace transform of d psi dx. Hence, d psi dx is Laplace inverse of s capital psi s. So, from equation 5.46, we see that phi x involves Laplace inverse of s capital psi s, and if we substitute Laplace inverse of S, capital psi S in 5.46, we get small phi x as 1 by gamma 1 minus alpha into d psi dx. Now, d psi dx can be obtained from equation 5.44, and if we substitute d psi dx in 5.48, we get phi as given by 1 by gamma 1 minus alpha into gamma alpha into d dx of integral 0 to x fu by x minus u to the power 1 minus alpha du. Now, we know the well known relation of gamma function, that gamma 1 minus alpha into gamma alpha, it can be written as pi by sin pi alpha. So, using this value in the denominator of the expression given by phi x, we find that the solution of Abel integral equation 5.37, which is a generalization of Abel's integral equation, as phi x equal to 1 by pi sin pi alpha d dx of integral 0 to x fu by x minus u to the power 1 minus alpha du, as given by equation 5.49. So, in chapter 5 module 2, we have learned how Laplace transform technique can be applied to solve Abel integral equation of first kind. This technique based on Laplace transform can also be applied to solve Abel integral equation of second kind.